Here's a scenario that has burned every developer at least once. Your tests pass on your laptop running Node 18. Production runs Node 20. Your colleague uses Node 22. You push, the CI goes green on your machine, and then production blows up with a cryptic error that takes 3 hours to trace back to a Node version incompatibility. The phrase "works on my machine" is not just a meme, it's a real, preventable failure mode. Matrix builds exist specifically to eliminate this class of bug. Instead of testing on one environment and hoping, you test on all of them simultaneously before a single line merges. A matrix build is deceptively simple. You write one job, and GitHub runs it multiple times in parallel, once for each value you specify. Think of it as a fan-out. One workflow definition, 3 simultaneous executions, 3 independent results. The diagram on screen shows exactly what happens. A single workflow fans into a Node 18 job, a Node 20 job, and a Node 22 job, each producing its own pass or fail result. This isn't just convenient, it's the professional standard for any library or tool that claims cross-version support. If you aren't matrix testing, you're making a promise you can't verify. The syntax lives inside your job block under a key called strategy, and under that, matrix. You define a variable name, in this case Node version, and assign it an array of values. That's it. GitHub reads the array, counts the items, and spawns that many parallel jobs automatically. The naming is intentional. Strategy is where you configure how GitHub runs the job, and matrix is the specific strategy of running it across a set of values. Each item in the array becomes one job, inheriting the full job definition, same steps, same runner, different variable value. Now that GitHub has created 3 parallel jobs, each one needs to know which value it was assigned. You reference that value using the expression syntax, $, double curly braces, matrix.your variable name. In this case, matrix.nodeversion. When job 1 runs, that expression resolves to 18. Job 2 sees 20. Job 3 sees 22. You pass this directly into the setup node actions node version input, and each job installs the correct runtime for its environment. The expression syntax works anywhere in your job, in step names, environment variables, conditionals, anywhere you need the current matrix value. Here's the complete, copy-paste ready workflow. Name it whatever you like, trigger it on push and pull _request, and in the job you add the strategy block with the matrix. The setup node action receives the matrix variable, and you run npm CI followed by npm test. Save this as .github/workflows/ci.yml, push it, and watch the Actions tab. 3 jobs appear immediately, all running in parallel, each with its own node version. If Node 22 introduces a breaking change to a dependency, you'll see a red X next to that job while 18 and 20 stay green. That's exactly the signal you need before merging. Let's talk about what you actually see in the GitHub interface after your matrix workflow triggers. In the left sidebar of any workflow run, each matrix job appears as a separately named entry test, 18, test, 20, test, 22, with its own status indicator and runtime. You can click into any individual job to see its full step-by-step logs in isolation. This matters when debugging. If Node 22 fails, you jump straight to that job's logs without waiting through the others. You can also rerun just the failing job once you've pushed a fix, without burning minutes rerunning the jobs that already passed. When you add a second variable to the matrix, GitHub computes the Cartesian product every combination of every value. 3 operating systems times 3 node versions gives you 9 parallel jobs, all running simultaneously, all in one workflow definition. The critical addition here is using matrix.os as the value of runs on, so each job actually runs on its assigned operating system. This pattern is essential for CLI tools, NPM packages, and anything users install on their own machines. A test suite that only passes on Linux is a liability for Windows and macOS users. 9 jobs sounds like a lot, and it is, but they all run in parallel, so wall clock time stays close to running just one. The full Cartesian product isn't always what you want. Maybe Node 18 on macOS is a combination you know you'll never support, or one that consistently fails for known reasons unrelated to your code. The exclude key lets you surgically remove specific combinations from the matrix. You list the variable values that together identify the combination to drop, and GitHub skips creating that job entirely. In the example shown, we go from 9 jobs down to 8 by removing the macOS plus Node 18 pairing. You can stack multiple exclusions under the same exclude key, one list item per combination you want to drop. While exclude removes combinations, include does something more nuanced. It either adds a brand new combination that wasn't in the Cartesian product, or it attaches additional variables to an existing matrix entry. The most powerful use is marking newer versions as experimental. In the example here, we attach experimental, true to the Node 22 entry. Inside the job, steps can conditionally run using if matrix.experimental. More importantly, you can set continue on error to matrix.experimental, which lets the Node22 job fail without blocking the entire workflow. This lets you track compatibility for future versions without holding back your current release on an unready runtime. This is one of the most common matrix mistakes. By default, failfast is true, which means the moment any one matrix job fails, GitHub cancels all the others. That behavior makes sense for a deployment pipeline where there's no point continuing if one stage breaks. But for compatibility testing, it's counterproductive. If Node 22 fails and you cancel Node 18 and Node 20, you don't know whether those would have passed or failed too. Set failfast to false, and every matrix job runs to completion regardless of what others do. Now a single run gives you the full picture, a compatibility matrix showing exactly which environments pass and which ones need attention. The flip side of matrix efficiency is resource consumption. By default, GitHub runs all matrix jobs simultaneously, which is great for speed but can hit your concurrent job limit on the free tier, overwhelm a shared external resource like a test database, or overschedule a fixed pool of self-hosted runners. Max parallel caps how many jobs can run at the same time. Set it to 2 on a 9-job matrix, and jobs run in waves of 2 slower overall, but controlled. This is especially important if your test suite makes calls to an external API with rate limits, or if your organization has a fixed number of self-hosted machines that can't all be consumed by one matrix run. Sometimes you need a job that runs after all matrix jobs complete and needs to know what each of them produced. You can wire this up using job outputs. Each matrix job sets an output value via GitHub_output, declares it in the job level outputs block, and the downstream job accesses it through the needs context. The critical caveat: if multiple matrix jobs set the same output key, only the last one to finish wins, there's no automatic merging or aggregation. For anything beyond a simple scalar flag, reach for artifacts instead. Upload a JSON report file from each matrix job and download them all in the aggregating job. That pattern scales cleanly no matter how large your matrix grows. Let's make sure the core concept is solid. A matrix with 2 operating systems and 3 node versions, how many parallel jobs does GitHub create? The answer is 6, because GitHub computes the Cartesian product, 2 times 3 equals 6. A common trap is counting the total number of values, 2 plus 3 equals 5, but that's not how matrices work. Another trap is assuming 3 OS values were given when only 2 are listed. Always multiply the number of values in each dimension together to get the job count. That multiplication is the mental model that makes every matrix discussion precise. Congratulations on finishing the matrix builds chapter. You now have the tools to test across every environment combination your project cares about.